Ladies and gentlemen, please join me in welcoming our first speaker, Professor Chao from Zhejiang University, an accomplished scholar in robotics and control systems. Professor Xu is an IEEE senior member and serves as professor of mathematics and robotics at Zhejiang University. He is currently the associate dean of the College of Control Science and Engineering at Zhejiang University and the founding dean of Zhejiang University's Huzhou Institute. Today, he will deliver a talk entitled Deep Learning Meets Control Theory from PID-Accelerated Optimization to fluid locomotion and robotic autonomy. Let's welcome.
Wait. Wait. Okay. It's my great honor to come here and to deliver a talk this afternoon. So I never tried to give a speech like this long, even longer than my class. So I scrapped several things in my work, combined into my talk today. So the main title is Deep Learning Encounters Control Theory. And I have 4 parts. So the first one is I try to brainstorm in the connection of control and machine learning, which deeply influenced the industrial revolutions. Okay, because Professor Tsai just mentioned that he worked a lot on control theory, then you must know this. So in the first industrial revolution, and Watt, the James Watt, a Scottish engineer, invented the so-called governor to make a steam engine work stably. So before James Watt, there was steam engine existed, but it's not stable. Sometimes it could be blow up. Sometimes it could be stopped. So then James Watt invented this so-called governor to introduce the feedback for steam engine. Then the system can keep constant angular velocity. But he's an engineer, and he didn't know why it worked so well. There is another famous giant scientist, James Clerk Maxwell. So he wrote a paper in 1868 on governors. So even today, you look back this paper, it looks very familiar to your ordinary differential equation textbook. Then you see this is a very good story to find a problem, a challenging from engineering. Then physicists or mathematicians use mathematical tools to explain, even help or improve the solution. Very good, a very inspiring topic. So I would like to say, because I'm from control was the enabling technique for the first industrial revolution. Then we go, then the human being went into the second industrial revolution. And as we know from the high school classes, there are many things like electricity, steel, automobile, many other things because of the progress of power. So we have, at that moment, human can make mobile power. So it helped transportation greatly. So you can see that was the old cars, electric vehicle, airplanes. So during that time, those early transportation systems was not a simple combination of engine and aircraft. The most important to guarantee safety is the guidance system or the measurement and the feedback control. Otherwise, you would see many uh, maybe craft, maybe catastrophes. So that's the second story to say that the feedback played a very important role in powered mobility. And I mentioned in the first and the second revolutions that control and feedback had played important roles inside. But what is control? What is feedback? So there is a mathematician. So you see, mathematician is always the power to push forward the human progress. So Nobel winner, Winner, who is a professor in MIT, he wrote a book called Cybernetics back. I forgot the year of the book. So the subtitle of this book is control and communication in the animal and the machine. So you see, he drew a very future picture about the human interface or the brain and the computer interface many years ago. So, and it's almost built up the system from the low-level physics, measurement, control to the high-level human computer interface. So that's the story, or that's the situation we see today. And people can have a robotic arm with the human body, and the signal can pick up from your skin and processed by the computer to drive the robotic arms. So, and after many years later, there is a article said that the cybernetics is for the cyber world. So basically, I would say that the most important ingredients of cybernetics can be summarized into three problems: is modeling, control, and optimization. So, given the example that is very frequently seen today is the recycling a missile, right? So it's like it can be uh, simplified into an inverted pendulum. And that's the first modeling, even though you don't see the mass yet. But so it's like you try to simplify a complex problem into a simpler model. Then you come up with the mass. If you consider everything in the beginning, you get a huge model, then you can do nothing. So try to get the most important ingredients inside. Then you use the math. Okay, so then here we can use the Euler-Lagrange equation to model this dynamics. Then you have the linearization to give the model. Because the model, nowadays people forgot Newton. They only remember hinting, right? They believe that data can do everything. But I think the physics is also a very important part of human intelligence. So it's like the Chinese saying, 不管白猫黑猫，能拿出耗子就是好猫。所以 we should solve real problems use the combination of Newton and Hinton, right? If you do some reinforcement learning for this model, you may try like a 10,000 apples training. Then the system could be very fragile to be defeated by any disturbance. But if you use this Newton's law to build up a very simple linear model, then you can make it very stable. That's what you see in the campus. People can use a self-balancing vehicle in the campus, right? 自行车. If you use the pure data-driven model to train this, I promise you won't write that in your daily life, okay? So in this example, you see modeling, we use physics, and control, we use classical control algorithm for low-level systems. Then later on, or in the last, we use optimization to train, to tune the parameters. So the next one, so we are now in the middle of the fourth industrial revolution, is AI, right? So you see in first and the second industrial revolution is actually we deal with a physical system with mass, coal, oil to build up a system. And it's very nice, very glad to see that a deep learning is also like a machine. It is data, and this we use math, like we use neural networks, we use differential equations, including like ordinary differential equations or partial differential equations to be the evolutionary machine to process your data. Then in the end, you have the product to compare with the label to see how good the system is working. If the outcome does not match your standard, what can we do? We tune the control parameters. It's like the same, we produce or we process information in the cyber world, but the process is quite similar to what we do in physics. So as we say, physics or the physical systems cannot work without control, right? Like steam engine, it could be blow up. Then we may ask the question after I explain this. So I want to use some mathematical notations to emphasize that cyber or the learning machines is the analogy of the physical machines. So in the physical world, we use differential equations, maybe modeled by mechanics. So in neural networks, we use the discretized dynamical systems. So then in physics or in the industry process, you have so-called control to tune, to improve the product quality, right? Then here in neural networks, you can still have similar parameters to tune. So in philosophy, they are quite similar. One in our physical world, another one is in the cyber world. And it's very easily to see that deep neural network training can be modeled by a terminal value optimal control. Okay, So it's very interesting to make this analogy that processing data via mass machine is quite similar to the framework we do in the reality. So you have crude oil, coal, and other industrial resources. Then we have machines, reactors process this. So this is the industrial equipment, right? Then you have some secret recipes, right? Formulas or techniques to make your product unique. Then that's so-called 原料、设备和工艺. So we make an analogy in AI is that we have data we call I use 算料 similar to 原料 data. Then you see neural networks are your math machines. Are your math machines as I just talked that differential equations could be your math machine. Like a parabolic equation is the core machine for diffusion model, right? You can use hyperbolic equations with dispersion to do also generative diffusion in AI. Then that's the structure, that's the raw material. Then how do you determine the parameters? That's the learning or the training algorithms. So you see, both in the physical world and the cyber world, this is the common thing. You need to pay the electrical bill. Okay. So you see, in the first, the second industrial revolution, feedback is played a very important role. And in my opinion, that in deep learning, feedback is still missing. It's like, so error propagation is not feedback. It's very similar like you shoot a gun, 打靶. So there is aim maybe on the wall, then you pull your gun, try, see, not on the center of the aim, then you put another. 1, 2, you do many tests. So that's not feedback. What's the feedback? You know maybe that fire a missile. You cannot fire a missile like 10 times to say, oh, I know how to fire a missile, right? Why missile can shoot the target once, one shot? Because missile have a feedback system. It can manipulate the trajectory along the trajectory. So today, neural network is like put a student in a high school without any exercise and examinations before he graduates. So maybe after 3 years, the student is sent to the examination and he get failed. Then he has to go back to learn. Maybe after 60 years, oh, you are lucky you get the admission to Tsinghua University, right? So that's not what we want. That's not what we want. So I think there must be chance for us to introduce feedback to the learning machines. As I just mentioned, there are many opportunities to introduce the model, to process, to represent your data. For example, diffusion model, we introduce diffusion or stochastic dynamics. So one way forward direction is the SDE. You add noise into the data. So you can model this use stochastic differential equation. And the backwards is to describe the distribution of the probability which can be governed by a parabolic PDE, is the Fokker-Planck equation. So who are the most community to understand, to know this, is a mathematician and a physicist. Then people in computer science just follow this from math and physics to come up a very powerful formation or pattern for this area. And I have to, I share 4 points here. This is what I just mentioned, that the machine learning nowadays, or the error backpropagation, is truly an iterative learning in an open loop way. And as I mentioned earlier, that the neural network can be considered as a discretized system, right? So sometimes you can always see that sometimes you are not lucky to see the gradient is vanishing, 梯度消失, or sometimes you encounter instability, which is that the gradient explosion. Why is that? You see, the solution for this, if this is right? So you just take a look at the poles. 极点，蔡老师知道，极点 poles, right? Or the eigenvalues of A. So that's the stability. And so in AI, people try to fix this problem, try to come up very, very complex models without using any ideas from feedback. Then I will show today that some techniques, very small techniques from control theory, can be used to solve this problem. Okay, then how to design feedback control mechanisms, or how to come up new structure to represent the data to enhance stability and accuracy. So this part could be considered as a control, is how to design the structure. So in the end, how to determine the parameters, that's training, or in control is optimization. Okay, so today I would to have to share mainly two work. Is first how to add PID control to improve the rigidity of neural ODE. The second one, how to train a large scale model using control ideas. Then I will share some applications. The first is the rigidity and feedbacks for neural networks. So you see, this is what we see in neural network. You have a discretized model. So for deep learning, you have many, many layers, right? So in computational math, which is the approximation of continuous ordinary differential equation. So for modeling, the neural network is not the unique option for us to deal with, to represent the data. You can use ordinary differential equation, even partial differential equation, because you have to have some machine, either from physics or from your mind-made neural networks to represent the data. Then learning is try to compute your image or data. Then in the end, you compare this with your label, with your standard label. So then that's the link that we can choose whatever you like to represent your data. So then you have discretized or discrete difference, ordinary difference equation or ordinary differential equation. So that's the dynamical system point of view of the information transition, how information evolved into your math machine. So that's the, in ordinary equation, that's the method that you solve, right? The parabolic mapping, parametric mapping, or the parametric flow. And because I like the ordinary differential equation more, or this is the easier. There are much richer tools can be used for mathematical analysis. So I choose ODE. So this was a famous work by Richard Chen Tianqi on neural ODE. So see, you name it. You can use any model to model this. So he just used the ordinary differential equation to model the process for data to flow. And but his background is not control. So for such a model, in computational mathematics, we can define the rigidity coefficient for this dynamical system. And then you can see for his model, and this output or the state can grow dramatically. It's like this. Even you have a small perturbation, it could go increase quickly, even blow up. Then you have to very carefully to deal with the initial value. You get a bit scared, and maybe you are lucky and you are not lucky to repeat it. Why is that? In sense, this is not stable system, and you have to introduce feedback control. You know, in the self-balancing vehicle is like a inverted pendulum. You know the SpaceX, right? The missile. It's not stable naturally. You have to introduce feedback control. So like this self-balanced vehicle, if you don't have a control system, it will fall down. That's the case for this. And how can we improve the high rigidity for this neural ODE in general? And before we solve that problem, we use some mathematical notations to calculate for this model. So we introduce a second order ODE for this neural ODE. Then we compute the rigidity coefficient, or simply for a linear system, the eigenvalues of the systems. And you can see the rigidity are strongly dependent on the structure on your network. Okay. Then how can come up a general solution for the system without deal with this highly nonlinear network. Okay. So we come up with this idea that can we introduce a feedback to this? This is called the PID control, and this is the differential equation like this. So it's your neural ODE for this. That's your math machine to process your data, and this part is the training. So this this is not a thing in machine learning because they have no idea about the control theory. So we just simply borrow the exercise from feedback through this to make a combination, right? A combo of undergraduate control with the neural ODE. Then that's it. Now we do the same thing. We introduce a PID as a control to the network. Then we try to recalculate the pose. Okay, and you see the pose can heavily dependent, or the rigidity can heavily dependent by the parameters. So that's like the PID controller can be used to control many things. So PID, P is called proportional, I is the integral, D is the differential. That has been used for about maybe about 100 years. The philosophy is very simple. P is when you take a shower, so you measure the temperature with your skin. If it is hot, then you maybe you turn you tune your the valve, right? I is the integral back to some time, so it's the history. D is differential, is you look forward the derivative. So PID for the very simple fundamental control is today or present, history and the future. In 赵本山，对吧？昨天、今天与明天 ，very simple, a linear combination of yesterday, today, and tomorrow. Then that's it. You don't have to worry about the model. Okay, then the last is the how to train the model. That part is like the technician, not many thoughts. Because when the model is determined, then how to train this is a dynamical optimization. You use computational optimal control. So you represent the derivatives using adjoint states, and I think this part has been fully discovered in computational math. Okay, here you can see the gradients of the loss function with respect to the parameter can be governed by this. And the structure of the network is determined by F. With the machine is determined, you have no more chance to retune it. Okay. Then we can analyze the evolution of the gradient, and you see with this feedback, the rigidity, the stiffness can be improved much better. Okay, so in another sense, the stability of the process to dealing with the data has been improved greatly. Okay, and for long sequence learning, if the gradient goes to zero quickly, then you have this gradient diminishing phenomenon. So how to make this goes to zero slowly? Then we analyze this the gradient A, And we find that we can use PID to tune the gradients of A, then it can help us to deal with long sequence learning. So that's an example for the humanoid walking. That's a very long sequence, and you can see without introducing PID, it goes to 0 very quickly. And here we can we can delay the gradient diminution for long sequence learning. So you can see we can introduce feedback rules, feedback control to help design the structure. So I only use PID. That's the first year undergraduate feedback control. Imagine we have a huge bank of control theory, like a differential geometry control for nonlinear systems. Then those can be tried to improve your network stability and accuracy. The second part, as I mentioned, is when the model is done, can we how can we train the network efficiently? So that's the process, as I mentioned. So, but finally, you have the optimization for those parameters. How to tune this, and you know the fundamental physics, fundamental math for this is optimization for large-scale mathematics, computational optimization. It's like you try to find the optimum in a very high-dimensional nonlinear space, right? So then you come up with gradient method or stochastic gradient method, and this is very very highly cost, and that's the reason why deep learning needs a lot of power energy. So how to accelerate the training process? But you see that the structure is the most important part. If you come up a poor model, then you may waste a lot of effort to make up your first effort. Okay, so geometrically you can see that the landscape is complex, and for high non-dimensional optimization is a big optimization problem. And the challenge is that the center points is very easy to track your numerical iteration. And when the points goes to the vicinity of the optimization, then the training is slow, and the training cost is very high. So can we do something for this? Because this, as I mentioned, the math for this training is optimization. And I'm in control engineering, and the optimization is not our first priority. So someday when I looked at this iteration of the optimization process, I failed maybe 2 years ago in the National Day holiday. I looked at this picture. I felt very exciting because you can see that for the optimization, the physics was cut off. People don't care in optimization. They don't care about the physics. So I think we should return physics to these dots. So it's like the valley. You put the mass in the middle of the valley, then the gravity will gather these points to the equilibrium. And the equilibrium has a strong connection to the optimality, right? So if you give physics to these points, then you have mechanics. Even you can have quantum mechanics to do this, because quantum can have some probability from one well to another well to help you to find a better optimizer. So that's something I call the science for AI. Not only AI for science, okay? So, and why we don't do this? So we consider the first part using classical mechanics first. Then what's the physics inside? If this is a mass point on the valley, we can use high school force analysis to understand the force gradients for this ball. So there's a free frequency, right? That's the normal force. That's the gravity. Gravity is the general gravity of the cos function, or the cos function, F. So then you can see you can use this high school mechanics, see, to build up a nonlinear equation for this ball falling in a high dimensional space. So that's physics. And if you do the discretization to solve your differential equation, then you have this so famous optimizers. So why I finally understood this, because of this name, heavy ball. I think the Russians, especially Russian mathematicians, they never separate mechanics from math. They call the math and the mechanics department. So I think this is the benefit of this tradition. So then for me, so now Russians introduced heavy ball for this. Can we introduce control? It's like you ride a motorcycle. So Russians closed down the engine, and it flowed in the middle of the mountain and then to a small valley, and that's it. If you turn on the engine, just shoot the engine, you can jump out. So that's the control. So then we can introduce a control for the heavy ball model. So of course, as I mentioned, there are many benefits to introduce dynamical systems driven by physics, because you have many mathematical tools from dynamical systems to analyze the convergence and the solution. So for example, we take a look at this heavy ball. That's something motivated me to understand this in a physical way. So that's the continuous heavy ball model using our high school knowledge, and that's that discretization to get the algorithm you see in the papers or in the PyTorch platform. And I will quickly go through this, and you see there are some. So that's for the discretized analysis. You have to come up. You have to come up very smart design for the compress the mapping to analyze the convergence. But in continuous, we can use ordinary differential equations, and Lyapunov function to analyze the stability from many tools from math. So how to come up with the control law. How do we design the feedback law? So I just tried the very simple idea. So now this is not a passive mass point. I call this a mass robot to explore the minimum point in the mass world. Okay, so how to give the protocol to navigate this robot. So we use today, yesterday, and tomorrow. That's called the PID to shoot into this to represent the control law for this mass robot. Then the rest is to understand the closed loop behavior of the system. So, and after many mathematical analysis, we have the convergence for the gradients and this strange one, a new feature that's the integration in the time window for the gradient. That's not existing for classical optimization. So what's the benefit of this? So what's the benefit of this? So before that, discussing the benefit, you see we use a control theory to describe the hyperparameters for the stability from control. How to tune PID to make the second order differential equation stable. Then you have the two convergence. One is the gradient, like what we do in optimization. Another one is you have this. Is not only you go to zero, but also you stayed in zero for a time window. So what's the benefit of this? In optimization, they try to use many ways to escape from saddle points. Here, you see, for this condition, you need a period of time to stay in zero. Then it can help you to escape from saddle point. For example, you ride a motorcycle to go to the valley. So not directly go to this maybe a saddle point. This one goes to if you don't have this, the delta F goes to zero. If you go to the valley directly, but with the integration, it's very interesting to see you go around this saddle point for 1 or 2 cycles, then escape. Because why? You have some part. You have some part positive. You have some part negative. So then you check. This is not the case. We must go. Otherwise, you are trapped by saddle points. So no any other fancy skills. Then just PID can help you to break into saddle points. So we did some testing, simple testing using those nonlinear functions, like a Rosenbach functions. Here we just solve this dynamical systems, ODE, to get the trajectories. And there are many benefits to see that this red line is our algorithm can jump out from the local minimum to the global minimum. So we can tune these PID parameters to get a very good results. And also it can escape from the saddle points quickly. So that's the heating time we estimated. Okay. And so for these simple models, you have these analytical expressions. Then you can solve this, use ordinary differential solvers. But for large scale neural networks, you don't have an easy expression to form this, right? So you have to do numerical analysis. So then there is so here you see symplectic geometry helped a lot because we come up this continuous idea to form up a neural ODE, and the mathematics in math is very beautiful. But in the end, when you do the numerical computation and you lost the benefit, we didn't know why. Because your numerical discretization introduced your artificial friction or dissipation to the numerical algorithm, and you lost the benefit that you got from the physics. So in my master's degree, I read a book on symplectic integration, and I asked my student to try that. And one night later, he told me that it worked. It's very exciting. So then, because you use a second order, is a mass point for this, so it's a mechanics. Then you use a symplectic to solve Hamiltonian systems, and you really benefit what you discovered in the continuous time. So in our package, so this is released. You can download this optimizer to try in PyTorch. And the solver, the solver is the scheme was written in a symplectic integration. So of course we tried many cases. So on some data sets like a Minsk, fashion Minsk, and a CIFAR 10. So and also we try to solve some simple equations like Burgers equation and Navier-Stokes equation, and not Navier-Stokes equation for this one. So Burgers equation, and we also tried for some large language models to see the high efficiency of this method. So here we can see it have a very good comparison to comparing to other methods. I won't go detailed to this because I'm close to the time. And in summary, so we return physics to optimization. Okay, then we use cybernetics to come up control law to improve the physics. Then we use like a symplectic or computational methods to come up these schemes. And these schemes is the new optimization algorithms. And you see this method can, so I will give you a very exciting thing to see that so if you use current, it's heavy ball. If you use current and the future, it's the Nestonov. So all of those famous solvers are the specific simplified version of PID. So we don't borrow any tools from optimization. We reinvent these algorithms use control. In the last day, I will go very quickly what we do in robotics. So because I do drones and underwater vehicles. So there is a interaction between rigid body and fluids. So how to model this instead of solving this Navier-Stokes equations, we do imaging. So high-speed cameras to see this field. So this is very interesting example. You put a cup of coffee here, and then you put some backgrounds pictures with noisy dots on the picture, and then put cameras here. So because of the temperature of the hot coffee, and then you see this the picture on the background. Then use this background to reconstruct the fluids. Okay, and that's the PIN's work. So we come up the images and the neural network for an Navier-Stokes equation to combine Newton and Hinton. Right. This is so we very exciting. We follow the optimal transportation. This mass tour to describe very high density particles and to get this large scale particle tracking velocimetry. And so also we have some experimental testing in the water. And the second one is the autonomy for drones, but this is not quite close to, because the first part is the tool, so it can be applied to many areas. I also work on robotics, 就具身智能 embedded AI. So you see in robotics there are many mathematical models like a localization or the trajectory planning and the registration and also this navigation. You really solve the second order conic program in real time in your machine. So you see, we after 10 years effort, we can compete human FPV flyers. So we use computational geometry, optimization, and to solve on board, not on your computer, on the drone. And we borrowed some tools on differential geometry is differential flatness to accelerate the to solving the rigid body for a drone. So to make it realizable in real time. So that's the experiment in the virtual simulation, and we can also transfer this in the real world. You can see this is what we fly in the underground garage without human manipulation. So that's a drone flying in the underground. So you see, to compute the trajectory for more than 300 meters, only using 0.26 seconds on board. And this is outside of the lab. So that's in the forest that we did several years ago, and we are very honored to get this the award from this conference. So this is really a truly combination of robotics, intelligence, math, and physics. And this is what I would like to share today. Thank you very much.